Ooh. Okay, yeah, looks like we're doing pretty good. Hello. Chat boxes. It should be up. I'll have to just keep track of chats. There we go. Which one comes through? Or why the YouTube doesn't. Okay, welcome. We're probably going to start in like 4 minutes, but we'll just make sure the stream is healthy, audio is working, and we have no technical issues. If you would rather watch on Twitch, this is also being streamed on Twitch. The VOD should be available on Twitch and YouTube afterwards. So don't feel like you need to hang around the entire time to get the whole content. You can review it later anytime. Oh, that's kind of annoying. The Twitch chat is at the top and the YouTube chat is at the bottom. Feel free to like, subscribe, follow me on, I don't know, X, Twitter, LinkedIn, or Twitch to keep up with content. So this is kind of a new board. I got this probably a few months ago. I recently got the mini PCIe expansion connector, whatever adapter, and so I was able to get it up and running probably last month, but I'm confident enough in the design that we can start looking at it. Also got the programmer for it up and running as well. It took a bit of time, but we should be able to look at the PCIe, look at some soft processors, look at some high-speed SerDes on this card, and hopefully do that over the next like 2 months. Okay, so we're gonna probably start in like 2 minutes at the 9:20 time listed, but feel free to say hi, where you're from, what you're interested in. Are you a normal microchip user? Do you use other FPGAs? Yeah, just feel free to add some stuff to the chat and we can talk during the presentation. Feel free to ask questions. Feel free to join the conversation anytime. We'll probably have, I don't know, an hour and a half long content. Probably won't go further than that, but hopefully we can walk through how to set up the PCIe, I guess, how to run through the PCIe example that comes with this hardware. Okay. Hello, I am FPGA Zealot, and today we're going to be doing a live stream looking at the Tinybeast FPGA, which is a Polarfire FPGA. I'll have to see what variants. We have a 300T variant, but I want to make sure, look at the product page to see if there's any other variants available. So the Polarfire FPGA is developed by Microchip. The mini PCIe accelerator card is developed by Sundance DSP. So the agenda for this simple little live stream, we're going to go over the hardware. We're going to go over the block diagram for the design on the Polarfire FPGA, and then go into the Libero tools and look at the block diagram, go through the components, look how they're configured, how they attach to each other to understand how the design works. It's a combination of RTL and IP blocks in like a two-dimensional block diagram. Then we're going to look at the example software. This is like the driver and application software that comes with the microchip PCIe examples. We won't be able to run the driver software, but we're going to look at the registers and how the registers map and how they work. And then we're going to toggle those registers through some direct memory accesses in bare metal and in Linux. And that's going to be our demo. Our demo, we're going to go through bare metal, twiddling of the various registers, bring up Linux, use Python to memory map the PCIe, read and write the registers, and try to initialize some DMA. Okay. Some quick disclaimers. This is not a sponsored live stream. I just chose to pick this content and I enjoy presenting it. I am not employed by Sundance DSP or Microchip. I did ask Sundance DSP to loan me this board so I could explore its features and evaluate it. I cannot offer any official support for these. You should go to the vendors to get that. I love to talk about projects, ideas, ways to use FPGAs, so the content for this channel and this live stream is for informational purposes only. All the opinions expressed are my own. So we have the Tinybeast FPGA. We'll look at the Crowdsupply page in a few minutes. We have two variants. We have a mini PCIe, and then we have one that has like a backplane or a connector that connects to a daughter card. And we can look at the Crowdsupply page to get a few more details on that. So a quick comment on the mini PCIe connector I'm using. I tried different ones to connect to a M.2 connector. The top two are phone mini PCs. They do not connect the PCIe lanes, so they're just doing like UART or SD or some serial interface. Those do not work. So you got to be careful when you look at a mini PCIe converter. They don't connect all the lanes. And it's really hard to look at a picture to understand what lanes the PCB is actually connecting. It's a little annoying. Some other platforms I want to look at in the future. I want to try this on the Raspberry Pi 5. So this hardware supports one lane Gen 2 PCIe, which is exactly the same thing that the Raspberry Pi can support, the Raspberry Pi 5. So this accelerator is actually really perfect for a Raspberry Pi type application. So I want to look at doing that. You get a generic PCIe to mini PC connector. There may be some modifications, but hopefully if you do get this hardware, there's appropriate instructions for being able to use these different interfaces. On the bottom, we have the RISC-V board. It's only like $80. It's called a Banana Pi or something like that. It's an $80 RISC-V processor and it has mini PC on it, which would be a fun board to try as well. So I might look at demoing that as well. Okay, so let's go look at some of the main content. So this is a Crowdsupply program that will launch soon. I do not know the dates. I do not know the prices. But they will be offering two Polarfire options. I believe they are both the non-SoC variants, so just the flash-based FPGA with 2 DDR modules and a flash memory. That flash memory looks a little bigger. This definitely has, actually, no, there's the flash memory. Not exactly sure what those are for that one. Okay. Here's a daughter card for the one that has the connectors on the back side. You get, SFP, PCIe, FMC, video out, SD card, Ethernet. So pretty nice. Let's see, was there a difference? So we got DDR. Oh, I wonder, they might be able to reroute the high speed from the FMC to the other components. We'll have to see what their schematic. So yeah, this is open source, so we should be able to look in the open source schematics when the campaign begins. Okay, yeah, so that's this. So let's go look at what we can do with the mini PCIe variant. So the reference design we're going to be looking at is AN4597. So if you want to look this up, this is the example design that we'll be going through for this Polarfire device. It has some slight modifications to fit the hardware. There is no DDR3, there are no dip switches, there are limited LEDs, and no push buttons. So this is, and no UART, right? There was like a UART connected. Yeah, there was a UART right here. We are not using UART as well. But this is the design. We have our endpoint PCIe. It's down to 1 lane, not 4 lanes. And we are going to be able to communicate through this to the various interfaces, which basically come down to local memory, external DDR4 memory, and some I/O control for the LEDs. There is also an additional DMA controller to transfer between the LSRAM and the DDR4, but the main DMA controller is in the PCIe IP core, which is able to do DMA from the host PC to the various memories on the board. We'll see if we have time to be able to go through those DMAs fully. Okay. Now we're going to move to the Libero design for this. Yeah, there's no hard CPU on this design. This is purely FPGA. But that doesn't prevent you from going to the catalog and pulling up a processor. I'm going to have to remember which one is the one they suggest. But there's a bunch of soft processors that you can load onto this device and be able to run things. But you do not have hardened processors, and so you can't like run separate. You can try to run Linux on the soft processor. I wouldn't suggest it, but you don't really have a hard processor dedicated for Linux. Okay, so let's begin at the top, and we can, it's the memory map. Memory map's pretty basic. We can talk about this later, I guess. So we're going to go first dive into the endpoint component. And this is basically the PCIe, our ref clock for PCIe, and device init, calibration, status. Okay, so these are just some system signals as well. A debounce. We don't really have a switch. So what is this even connecting to? Is this just like blank at the top level? Switch. Where's the switch actually connected to? Oh, it's disconnected, so it's grounded. Switch is grounded. So no switch for this one. Okay, so let's go open up the PCIe. Basically, all the Polarfires and Polarfire SoCs have the same hardened PCIe core. So what you see here, you can do on any different PCIe, any Polarfire FPGA. It's kind of across all the variations. So we have 2 of these, and we can do endpoint root complex. We can pick the number of lanes and the speed grade, Gen 1 or Gen 2. And we can pick, we can actually have 2 PCIe root complex or endpoint, so that's really useful. The Beagle v Fire can actually support 2 PCIe devices, even on that small of a board. Hopefully we can demo that later. Identification, this is useful. This is Altair, or not, this is Micro Semi. I can't remember what's vendor ID this is. This is a basic device ID. I added this class code. You need to have a non-zero class code if you want to have the memory enumerated in Linux without a driver, which we're going to do. So if you do get this design, I would suggest modifying the class code so it works within a Linux instance. I don't think what's the useful thing? Yeah, I got a bunch of different options there. Interesting. So that's okay. These are the 2 bar spaces. So when you have PCIe, you have, I guess, you can have multiple bar spaces, and these bar spaces will translate to addresses within your system. they don't need to be memory mapped to memory map. Other FPGAs will do address to stream, where the Polarfire does exclusively memory mapping on the first generation, um, but it does this different translations per bar. And we'll actually see during the demo that we can dynamically change this translation inside the PCIe core. Okay. The slave settings, this is more important if you're doing a root complex. I don't understand too much about doing the root complex. It's one of my to-dos to learn more about that. But that's, in general, the PCIe core. So we get one AXI master, and it's going to be using these two addresses. So let's follow this AXI master bus. So this AXI master bus goes up here, and it's going to this interconnect, and it divides up. It has 3 masters and 5 slaves. So let's go look at this component. Oh no, 2 is actually dead. Okay, we're gonna go here. This is the important part. It's a little bit hard to read. That's okay. If you do FPGA tools, you know you need to have like a 4K monitor to be able to see everything effective. And I can't really stream 4K resolution. It doesn't really work very well. Okay, so we have 5 different slaves, and they're basically going 0, 1, 2, 3, and 4. And if we look at where these are connected to, this, so this is basically counting these ones, 0, 1, 2, 3, 4. Okay, so 0 is going straight to the PCIe. So this is going to be able to change our configuration of the PCIe dynamically, and also initialize the DMA core inside the PCIe endpoint. So the next one here, the 1, hello, Kristen. So the next component, on Casey Nelson, hi as well. Yeah. Have I seen scaling with the Xilinx tools? I mean, it usually works pretty well on the 4K monitor. I mean, the text doesn't scale. The GUI does. So you gotta like look at where the text is hard to scale. I do agree with that. Okay, so Axie Master or Axie Slave 1 is going to our IO control. Slave 2 is going to where our DDR3 would be. Slave 3 is going to our local SRAM, and slave 4 is going all the way to our memory controller. And then we can see the address space for these components by clicking here. And it's basically we've assigned 256 megabytes, filling the full address space for each of these components. We have like 4 gigs of DDR, so it must be limiting the DDR. Let's see, let's click the DDR core and see if anything pops up. Pretty sure we have way more DDR space. Okay, I don't want to change the core right now, but I'll have to look into what the actual configuration of that is. Okay, so most of our fun examples are going to come from this Axie IO control, which is just some Verilog code. We have these test registers. Okay, not test registers. We have these system registers. We have a basic read-write register, which is just test register there. LED address, dip switch, DMA control, clock count, DMA size, the PCIe DMA size. Oh yeah, there's a UART and a for DMA size. I wonder where these things are going. For DMA size is going there. And the PCIe DMA size. Where is this actually going? Okay, if we go back here, mostly, okay. Where's that DMA side go? Oh, does that even do anything? You got to register? Okay. Signed there. Written there. Interesting. And then it's monitored. Yeah, I don't really know what that one's doing specifically. May have to read the documentation. Okay. And we can look at the DMA core real quick here. So these discrete signals here, the size and the start, go to this AXI, this kind of Verilog AXI DMA controller, and it's doing very basic DMA transactions between the LSRAM and the DDR4 over here. This doesn't do any PCIe DMA. This is only local DMA between the internal and DDR memory. Okay, I think that's it for the block diagram. We're not going to build this today. It's already programmed. We're not going to try to do this from scratch. If you want to open it up in your version of Libero, go to the right here, download the zip file, and you can look at it yourself. Okay, so now we're going to jump into the software for this. Okay. So here is our main application. We're mostly just going to look at the LED. Oh, where's the menu? Okay, here's the DMA menu. We're mostly going to look at the LED option. I'll do maybe device info, LEDs, and the read write to different bar spaces. Okay. Let's just grab that information. Okay. So the LEDs, we're going to the LED glow reg offset. And that's pretty easy to follow. If we go to the H file here, it's register 8. If we go back to our Verilog file here, it's register divided by 2. Okay, here it says 8. There. Is it 64 bits per? Yeah, it's interesting. I don't think. Yeah, are they doing 64 bits on the bus? Data. Okay, read data, write data. Really weird that they're doing 32 on one side and 64 on the other. Okay. The documentation is kind of all over the place, right? So we have documentation for the PCIe core. So that's here. This is the full PCIe core. Where it talks about the different options you have. Where's the good picture right here? With the DMA engines, the translation, the configuration. And then you go in and you're like, okay, how do I connect to it? There's example driver software right here, right, that talks about the different registers you're reading and writing to. But you're like, okay, so you have these registers. Where did you find these? Where's this value come from? But then if you go to the device register map, you go to the page instances, and you look at the offset, which is right here, 300800. Let me show you where this comes from. We go back to the block diagram. We go back to the axis, the APB. There's actually an address translation in one of these cores that goes from 0 to 30. Let me see if I can find it. These. That one right there. Okay. Go to memory map. Looking at the 0, 0, 0. Okay, it happened somewhere, right? Where it's being translated from this 80C and it's going into this address space here. Hello, Lewis. So then you go to the PCI bridge here, and we're going to find register. What's the fun one? Let's find. So there's a special register. If you go down to the memory rights, the DDR LS RAM shift register, and that should be here, and it's 8648. So we go back to our large register map, go 648 right here. We can, this is the translation register for the bar 2. Okay, so what we're doing here with this register right, we're changing the translation address for the second bar space. And you got to follow the software, the IP block, the register map. So it's a little bit of a puzzle. But hopefully you're using their driver software and their information that kind of just does this for you. But it is a bit of a treasure map to find everything. Okay, so we have the LED rights. We have the simple DDR shift where we change the bar 2 address space and do generic reads and writes. Okay. There's a lot to go through here, but let's go look at the bare metal example, and we can walk through it a little bit. Okay, actually, let's look at the hardware. I forgot to show you guys the hardware. Boom. Okay, right. Okay, so on this hardware on the screen, right? Can you hear me? Yeah. We have a Avnet ZU board that's going to act as our root complex for using the processor PCIe, and it's going over to an M.2 A E. No, it's an E. Yeah, it's an E key, and that E key is being translated to mini PC, where we can talk to the Tinybeast FPGA Polarfire over PCIe. Now, okay, cool. See how long it takes for the stream to catch up. Oh, not too bad. Twitch is a tad faster. Focuses. Okay, cool. So, now we're going to go ahead and interact with it in bare metal. Okay, so this is our PCIe communication, and let me see where we're going to go. So we're going to walk through what's happening. So we have 2 bar spaces. One is this is 64-bit addressing, so the addresses are actually really large. So this is going to be bar space 0. This is for interacting directly with the PCIe configuration. This is bar space 2. And even though we have, large LS RAM or large DDR, and we can't, talk, we only have 1K of size that we can talk to, what we can do is use bar 0 to change where that translation is happening. So we can effectively communicate the whole location using kind of like a page table with the translation option inside the PCIe core. But we're not going to do anything terribly fancy with that. So kind of what to expect. We're going in here and we're going to read bar space 2, offset 100 hex. This is going to the RTL in the IO control, which is, here. And we're reading address demo type register. And we, look that up. Look at this. So if we read this register, we get 332211. And let's go ahead and run this board. Hopefully the JTAG works the first time. Oh, looks like it's working. Cool. program the zinc, load the software into the ARM processor, look at the output. Okay, so right here, we are reading address 100, and we get 332211. Now we're going to interact with the read-write register. Go back to the Verilog. The Verilog has the read-write register at address 0. This is a very basic, read-write component. You can read it, or you can write it, and you can read it. Very basic. So here we write 1, 2, 3, 4, 5, 6, 7, and we read it. Okay. The next thing is where we actually start interacting with the translation table in the PCIe endpoint. So here we're using bar space 0 and that inner address of 8648, and we're changing the translation from 10000 to 3000. This allows us to interact with the LS RAM. It says deadbeat both times because I didn't zero it out. Let's go ahead and kind of zero it out. Right here. Where's the fun writes? So we do a read, we do a write. We can go ahead and like zero that out. There, we'll rebuild and maybe rerun in a second. And then we go back to our default IO control space using the translation address. We can change the translation address to DDR4, do the read write again. There's that translation. We can put this here. Okay. Yeah, go ahead and rebuild that in a second. And then we do the LED test. We missed it on the screen, so we're going to rerun it and show the LED test. But first, we're going to build this boot. Okay, we're back. What in the world happened? My computer did like a restart or went to sleep. That was weird. You guys still hear me fine? That was weird. Okay. Yeah, I unplugged the USB and it went into like a hybrid sleep. It like went into sleep. That was like the weirdest thing ever. Okay, cool. Um, let's let's go ahead and run this and then get off of trying to So let's turn on the full screen mode and we can look at the LEDs. It'll be so fun to watch the LEDs real quick. And then we're going to pull up Linux and Python and try to interact with the PCIe core a little bit. And if we get time, we'll try to get the DMA core up and running. Okay, so cool. Here we go. LEDs are off. Okay, red LED turned on. Green LED turned on. Okay, both LEDs turned on. Okay, so we're gonna boot this up into Linux and have a fun time. Relatively. Be booting into Linux. Let me track that down. Okay, there we go. Let's get the screen back on. You can watch Linux boot because it's so entertaining. This is Linux on the ZU board. Okay, so we have the Zinc board on the left, and we have the Polarfire FPGA on the right. So those are two. And let's see. Okay, so you records. Okay. Um, so my F config. We are at address 20. Okay. Or is it address 9? Definitely address. Okay. Okay, so we're gonna use Jupyter notebooks inside of XDMA. Okay, cool. So let's get the addresses. It's gonna be an ls PCIe-VEV, and we can see that we are at the same address as we were before, but they swapped. So that's bar 1 or bar 0, and this is bar 1. Okay, so we're gonna go here, and we're gonna run this demo real quick. Say we're gonna do like a bar 0. And we're gonna say bar 2. And let's see, this is 8. Okay, but a 6 here, 6 here. That one is different sizes here. Definitely, no, that's right. And that's going to be 6 there. So let's go try to read. We're gonna try to read bar 2, address 100. Oh, I didn't enable it. We might have killed it. We kill it. We just have a slave error. That's fine. Kernel. Yeah, I killed the kernel. I know. My fault. Okay, because we are using PCIe without, yes, this is the pink overlay on the ZU board, because we're doing and your buffer. We're going to sudo su. We need to manually enable the PCIe. So we go to sys, into devices. Definitely bus. Go bus. We're going to go PCIe. I go to devices. Going to be the 1. Okay, so we're here. There is an enable, right? So enable. So we're going to do an echo 1 to enable. This is going to turn on the device. So we do LSPCI DSP. We can now see that the device doesn't have a disable here. It had a disable before we looked at it. Ah, right. Okay, going back here, let's try this again. So now the address space should be enabled. Look at that. We are reading the address. Beautiful. So let's go ahead and get the LEDs running. Right. We're going to do the LEDs are address 8. So let's do bar 2, address 8, write a 3 to them. Okay. So let's do 1 beep seconds, right? Beep is not. Just import time. Do a block above and say beep in seconds. That's really slow. Let's do. I guess we can just do. Let's do half second. 5. So we're gonna like this. This for x in range 10. Run this. Now let's do this so you guys can see the full screen effect. Full screen. PCIe. Woo. Okay, we have an LED going back and forth. Yes, Lewis. So we have two FPGAs with a PCIe root complex and PCIe endpoint. So we have two FPGAs talk to each other over PCIe. And we're using Python to drive the root complex side. Okay. So we got that working just fine. Now we need we want to do. And talk to the address spaces. Let's try to get DMA running. DMA is going to be fun. Look up the pink instructions. Pink has a special memory. Just try NumPy then. Ah, that's what we want. Pink gives us a great little function called allocate. Give us a continuous piece of memory. Yeah. We want relay. Really have? Why do you need an overlay? Have an overlay? Shouldn't matter. We'll load in the built-in overlay. Should not be an issue. Okay, so we're going to load in the built-in. Okay. Now, will you allocate? Okay, you allocate just fine. That's going to bother me. Okay, so now we need to do a DMA transaction. So we want to do this between the let's do this between the LSRAM and main system. So if we want to do the LSRAM, we need to set bar 0. Let's go ahead and do a read, right, of the address bar 0. Okay, so right here we're going to want to read that at right here that twice. Oop. Okay. Next, please. Okay, so we want to talk to the LSRAM. LSRAM is going to be located at 3. So if we want to be able to read a large amount of LSRAM, we're going to need to do a bar right at that address 8 0 3 4. Okay, we now have the LSRAM defined. Okay, now comes the beauty of trying to get the do this transaction. So we want to do a write. There is DMA read. Look at a DMA write. To do a DMA config. Okay, so we basically want to look at these address registers here to do I believe a write DMA. Okay. So this is doing their driver. So the driver we're looking at is doing called gather. We've allocated memory into one unit. We're going to do a simple transaction, and then we're going to try to read it or write it. Okay, so we want to look at that it's when we start doing this bar info 0 base address plus local we'll have to get where that's coming from, but let's go ahead and set this up. So we're going to go ahead and grab this information. Okay, back to Python. Boom. And we now have all our addresses. That whole thing. Okay, so let's go back here and set up the values that we want. Back here, C drive. So we're going to want to the best way, like copy and paste, set it up. Okay, yeah, I guess we'll copy and paste and just slowly work through this. So we're going to do bar 0 write. Okay, and then let's paste this. Put there, there. event, figure out that value. Question mark. Okay. Next. Really wish I knew what values were. We can go hunt this up later and see what values actually do. Now this is easy. Buffer pointer. This is going to be the input. Which oh, let me figure out what the physical. Go look up the pink allocate. In GitHub. Here we go. There should be right here. Physical. A X. There's our physical add. Okay, yeah, we can do that. 32-bit. Good there. 4-bit address. 0. Nation. 4 is what this has to use the address of we should look at what values are added to this. Twenty-four matches. Okay. It's gonna be in a DM big here. Okay, right. Right. So if we're doing DDR3, okay, so it's just going to be the generic offset. So I guess we have to the full address offset here. That's just okay. So out all that the length. We're just length and what we're going to 2024. We have DMA control. First, where did we do that? That's weird. DMA length, DMA. Oh, this is bar 2 base address. Oh, that's going back to that is going back to Libero. Okay, that's what that's for. It's going back to this address? Yeah, 38 divided by 4. It's going back to that. Oh, sorry. I can talk a little bit louder. I'm probably just talking to myself. Oh, you're not able to see my monitor? Oh, sheesh. So embarrassing. Okay, this is what we've been doing. Got the address. We're doing the length thing. Remind me. I'm going to need let me put my to be able to look at this better. Okay. Let's not have that embarrassing. Okay. Ugh. Okay. You hear me? Let me see. The audio, I can boost the audio a bit. Boost. Okay. Okay. A little more. A little more. We can do a little more. Okay. 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 Now we're a little bit louder. I can definitely hear in my ears. Okay. So we have the addresses set up for the PCIe device. Have this. I think we can skip this, right? That's weird. Um, it's definitely having it set to okay. So they definitely having this set to yeah 1. For address for sure that's right. Yeah. So they were doing R2 right that. So R2 38 write the DMA length again. Okay, and then we want to write the control register, and that's just magic value, and that's the counter for the throughput. Oh, it probably has like a, does it have an interrupt going there? Arrow. Let's go back here. It has to be like a interrupt. A valid, ready. So we go here. PCIe. Where's that coming from? Valid. It is. Okay, it's PCIe access. Back to PC. Uh, breakout of that. I don't see where that. Yeah. Okay. Yeah. So it's doing it based upon read and write of system. Okay. So we have the control, and then they want us to clean and okay. That is DMA. We gotta figure out what the event values are. Let's go back here and make sure we're not seeing anything. Oh, it looks like it's reading the status. So let's go ahead and read the status. Actually, let's just do it here, right? Bar 0, right? Read status. You have the status register? Yeah, we do. Make sure status is 0. Let's do that as X as well. Okay. Below this, we want to set this to 3 for the LSRAM, and then we want to for do what? X range 10 X bar to the of X. Okay, cool. So 0. We need to look back here. Values. Okay. So that should magically change. Okay. So we gotta figure out what that is. Okay, let's see. Is that happening here? Not happening there. Okay, here we go. In there. Okay. So we have status, have this, mask first one. That's the these of this. So by that over here. Yay. Okay. There. Yes. No. Why that magical values that okay. Cool. Copy paste that back to here. Done. Okay. This input buffer. Okay. I'll do magical address. Okay. Status. Yay. Yay. We did DMA. We did PCI DMA. Woo. Okay. Let's interesting. We need to out. Okay. Let's so this we do what do we want to do? Sure. Yeah, we gotta do like okay. So I think we gotta do 0 by 4. Ah, Python range start. We want to stop. Okay, put a 0 here then. Okay. Really weird. Let's try that again. Five. Okay. Let's try something different. That over. Yeah, that's kind of weird. Oh, that's happening. But we did 1,000. Right? Okay. Yeah, 4,004. Is that the only one? That's where it ends. Data size. Um, where does this go? Okay, so DMA length. You do this times 4, 4. Okay, you got everything except that. What is that? That's a weird thing. Okay. Anyone know why DMA would throw a random value in? Weird. Maybe let's change location. Go 4, 4. Oh, I know why. We need to do this at the beginning of this. Do that. Okay. So we just DMA to the DDR. You can just oh 1004 x4 there. Okay, so let's write a bunch of zeros. So let's reallocate it. Reallocate the zeros. Write this. Now, so zeros, and then we can allocate cafe. And if we run this again, okay, so we have the DDR on the PCIe. We have the local buffer. We run this. We have now translated to the system. Okay, we've done DMA. Does anyone want to see or talk about anything else? Oh, I should say. Okay, if anyone joined halfway through or anything, we can go back to this. So we have the Tinybeast FPGA. We've demonstrated the PCIe design. Feel free to play back and run through it. We can walk through the software again because I didn't demonstrate that. But yeah, okay. Let's talk about what we're gonna do in the future and go through the software one again and then do future work. So let's say in 3 weeks, we're going to do the soft processor and program and debug over JTAG. So if you want to see the soft processor on this component, that's going to be like 3 weeks. Next week, we have a sponsored live stream from Altera in the Agilix 7. So next Friday, let's say next Friday, come watch the Agilix 7, and we're gonna go and walk through the Agilix 7 and get that system working. Other than that, we'll probably do Thunderscope the week after, and maybe some posts and streams in between. Okay, but let's go ahead and walk through this system. So, we didn't see this. We have a PCIe Actel device, Actel microsemi, now microchip. We have an Actel device. We have bar 0, bar 2. We used a enable command, echo 1 enable at this location, right? So sysbus PCI devices, we enabled it, and then we can do read and write to the device. And we have memory mapping. This is basically, we're going to take the raw memory address from devmem. We're going to map it to a NumPy array, set it to 32 bits, so it does appropriate word reads and writes. Set up bar 0, bar 2, read the test register, play around with the LEDs. Oh, I know why that didn't work. We need to do this back here. This. Okay, LEDs are working. Let me make sure I'm watching the stream so I see what you guys see. LEDs running. Great. And then we allocated memory space. We got all the special registers for doing internal DMA writes. We can do reads later, right? We have a whole list for reads, and it's probably very similar controls. So we could potentially walk through that as well. Nothing big at the moment. So we got the registers. We got the physical address for our beautiful buffer. We were able to DMA that physical address to the device. This is bytes. There's a status register that shows the throughput. I guess we can look at that real quick. So if we go back here, we go below here. We want to look at bar 2. Look at bar 2. That's very basic addressing. You ever read the throughput? Read the throughput. Okay, let's go back here. Here, the Libero IO control. No, this one right here. So there's do we read throughput? So if we write to address 18, what happened? DMA starting a DMA start register. Next, different A's start register. Where are we measuring? Yes, we look at where this play. There's a DMA counter. That DMA go. The ends. DMA progress. Okay, so we have DMA progress. Oh, that's it. Okay, it just has the DMA in progress. That's all. Or just, yeah, I don't see actual throughput measure there. Uh, okay, I don't know where you're actually reading this throughput status. Let's see. Okay, we actually reading. Is that going to be over here? Okay. Right throughput. Have a G5 frequency. Right part. You're saying address. It's the wrong bar. I'm bar 1. Yeah, maybe. Bar 5. That doesn't make any sense. That address. Right? Here. Address register. That should be 0. There's the clock frequency. Clock counter or something. Maybe. Okay. Okay. So we read the clock count. You can see how fast it. Okay. So where was the? Okay. I want to read the clock register. Okay. Where's this clock count? The address 20. We're almost there. Sorry. So below we're still in this thing. So we're gonna do bar to read address 20. 20 read X. Doesn't really make sense for the counter. This again. Just the clock count. And I guess we want to read address 50 as well. Just say 200. You just say 200 megahertz. That's all it is. And what you want to say right here is this divided by 200, do 3, do 3, 2 seconds. It took 2 seconds. Let's try bigger and better. Okay, so let's try, it was 1 kilobyte, let's try 1 megabyte. Okay, that's megabyte. Go ahead and do 1 megabyte. But it's not going to work. I guess we still can see. Okay, it says it took 10 seconds to do 1,000 more. Okay. Divided by data size times 4. This is going to be the bytes. No. We have 10 seconds. How many bytes in 10 seconds? Okay, that's how quick you do a byte. Ah, yeah. Is that value keep changing? Not what I wanted. Yeah. Okay, whatever. I don't know how to set the throughput, but oh, okay. Hi. So Dinas's boyfriend. There's a few previous videos or live streams where we go through building a CPU. I'm more interested in using existing vendor open source IP. So I'll usually look at Lidix. How do you implement a Lidix? How do you use like someone's processor integrated with like a Axia Alba bus? Are using the vendor processors. I don't really have, I would say, time or dedication to do a series on building up the Verilog or VHDL for trying to do a full system, testing it, and getting it running. I feel like there's a lot of really good examples, much better than what I can do out there. Okay, so I think that's really what we're going to do today. I'm excited. We got the DMA running. Um, Does anyone have questions before we call it a night? Uh, Next week, we're going to have a Altera sponsored live stream going over the Agilex 7 hardware. A week after that, we'll probably look at the Thunderscope. Then I think then we'll see what happens after that. But yeah, join me next Friday to look at the Agilex 7. We got a board. We're going to bring it up. We're going to look at doing LEDs in a soft processor. But that's it. Thank you for joining us. Please leave a like, a follow, follow on X, Twitter, Twitch, LinkedIn. Find me. Use my real name. Are on YouTube. Leave a comment. Offer suggestions. We'll do what we can. But yeah, thanks again, and good night.